So this video is going to come probably a little bit after the time of the lecture because I'm having interesting issues. The latest one being that the last time I recorded myself this way, the file was humongous, something like 30 gigabytes, and transcoding to make it uploadable to YouTube took forever. But anyway, this will come today. I mean, today being the day when this lecture is supposed to be given, and we'll see how it works. So I'm still on the computer rather than on the light board, and in this present instance, I think it's important because what I will be doing is going over a bunch of things and showing you the code to run some of these things at the same time. And I'll actually probably take a few steps back and go back to some of the notions we saw in earlier lectures and also illustrate this in R. Okay, so the first thing I want to do is, before I go any further, I want to say one last thing about degrees. And I mean, I say one last thing, but we'll see them again and again. But I mean, in terms of defining the topic and the content. So the last thing I wanted to do is to show you that degrees are actually very easy to deal with using the adjacency matrix. Sorry. And so suppose I've got an adjacency matrix A, and in which Aij is 1 if there's an arc from I to J, and not the opposite. I mean, this is a remark I should make. Sometimes you will see definitions of adjacency matrices where you would have Aij equals to 1 if there's an arc from J to I. But we're using the convention that the arc is from I to J. Just check, you will see things change just a little. Now, if you have your adjacency matrix, the good thing is that you can very easily obtain the degree from this adjacency matrix. If the graph is unoriented, it might be, well, I mean, you'll probably have to do some adjustment. But if it's oriented, directed, then it's quite easy. And let me show you. So if I have my adjacency matrix and I take a vector of all ones, which I'm denoting bold E here, then if I multiply my adjacency matrix on the right by E, so E being the column vector of ones, then what I get is the out degree. Okay, because remember, so I said Aij is movement from I to J. So the first row, for instance, of the matrix is movement from 1 to all the other vertices. And therefore, when I multiply this by the vector of 1, I get movement from 1 to 1 plus movement from 1 to 2, etc. And that is the out degree. And the same way, if I multiply on the left, then I get the column sums. But of course, if I multiply on the left, I need to transpose my vector E, okay, for the operation to make sense. But when I do that, I multiply by the vector of ones on the left, and I multiply the matrix here, then I get the column sums. And the column sums are the in degree. So we'll come back to this. So before I go any further, let me illustrate degrees with the graph that we've been using throughout, which is this graph here, where we have this sort of little triangle here. 1 and 2 are communicating back and forth. 2 has a loop. 6 has a loop. 5 is like this. And just for illustration, I'll also use the same graph without the loops. Okay, so this is exactly the same graph as here, G1 prime. The P is for prime. G1 prime is the graph here that has the loops removed on 6 and on 2, I believe. Yes, 6 and 2. It's a little annoying, just in passing, and this is something that you can address and then we'll do in the examples that are coming later in the course. You'd be happy, probably, to see those two graphs plotted the same way, because you can see here 6 has moved from being here at the top to being here. Okay, there's ways to arrange this, but I'm not doing this for now. But as I said, we'll see some of that later. Just in passing, I'll also be looking at graph G2, which is the same as the original graph, but here I've removed strong connectedness. Okay, so this graph or the graph above are strongly connected. Here I've removed strong connectedness by cutting the link, the arc, from 5 to 1. So in this graph, there is no strong connectedness, and that's it. Now, we had eccentricity, and I'll just point out that you can compute those eccentricities, and we'll come back to that. I just really want to point out how important it is to consider, to remember that if you're dealing with a directed graph, then the direction in which you follow the arrows is important. So because here you see the first 3 measures I'm taking concern the graph that we've been using as an example throughout. And you can see that the eccentricities of vertices in some, yes. So first of all, the eccentricity of the 2 graphs with and without the loops are the same, because of course we're not counting the loops when we're looking at how long it is, because any loop, of course, makes the trip longer if you want. If I were to go on 2 like this several times, I would have a longer trip than if I just traverse through vertex 2. Hence, there's no difference between G1 and G1 prime in terms of the eccentricity. But look at the difference between the out eccentricity, for instance, and the in eccentricity. And you can see that some vertices are the same. Okay, this one, the first one, and the 4th one, and those 2 are the same, but some change quite distinctly. Okay, and the same way, if I look at what is called all, so remember that in this case, when we have a directed graph in iGraph, when we say mode equals all, typically we think of the unoriented, undirected case. Okay, so here in the undirected case, the eccentricity is very different. Okay, so let's get to the degree now, because that's really where we left off the course the last time. So if I want to get the degrees, then again, because this is a directed graph, we can have the degree, we compute the degree, and it is very different if we look at in degree, out degree, or the degree in the undirected case. You can see that the in and out degree are essentially the same for 3 vertices, different for the 3 others, and the degree, the all degree, so the undirected case is much higher because you're ignoring the direction of these arrows and you're just saying, well, that thing here has 2 plus 1 plus 1. So I'm hoping this is, where am I? Yes, 2 plus 1 plus 1 is 4. So the degree of node 6, vertex 6, is 4. The degree distribution that I indicated in this slide here is something we'll see when we look at realistic graphs. Okay, the graph that I'm using for now as an example is really like it's got 6 vertices. It's not really important. It's just meant as an illustration. And so when we look at the degree distribution on this one, but it's still worth explaining briefly why we have a very simple graph. So remember, what the degree distribution gives you is the number of, well, the frequency. So this all these vectors, these results, they sum to 1. As you can easily see, this is 1/3 and 2/3, 1/3, 1/6, and 1/6, and 1/3, 1/3, 1/6, and 1/6. So those 3 results sum to 1. The first value is the number of the frequency of vertices with degree 0, so not connected to any other vertex. Then the frequency of each value that's coming up, potentially 0, potentially not represented, but how many times, how frequently do they appear in the degrees? So if you look at this degree here, this is the in degree for our example graph. There's 2 possible values, a degree 2 and a degree 1. So what this vector is saying is that there is never a vertex with degree 0, and then 1/3 of the vertices have degree 1. And indeed, if you look, there's 6 vertices and degree 1 comes twice. And then there's 2/3 of the vertices with degree 2, and that is here. Now, the second one is the out degree. And so here I'm saying degree distribution mode out. And so here we see that there's 1, 2, and 4. And this is what is shown here. There's 0 degree, 0, the vertices with degree 0 appear with a frequency of 0. Then most of the vertices have degree 1. Okay, 2/3 of them have degree 1. Then there is 1 vertex of the 6 that has degree 2, no vertex with degree 3, and 1 vertex with degree 4. And same thing for this one. You can see that this one goes up to degree 6. There's also the KNN, which I described briefly. Let me... did I? No, I didn't describe the KNN yet. KNN is coming later. Okay. I think... Oh yeah, no, it's here. Okay. Average neighbor degree. Okay. So we can compute the KNN for G1. Probably need to say works only with simple graphs. So okay, so this is one case where I have to use G1 prime, because remember G1 prime is G1 from which I have removed the loops. So the KNN of G1 prime, I believe I probably have to say, if there's something as mode, yes. So if I say mode in, those KNNs are going to be distinct, whether you look at in, out, or all. So in, this tells me what so that is, well, you can see that this one, for example, is doesn't have k nearest neighbor here. Okay, so this is what the KNN function gives you. Again, this is something that I will show you in a practical example later on. Probably next lecture we'll start looking at a real graph. Strength, I'm not going to show you now, because remember, strength is like, it sums the weight of the arcs or edges out of the vertex. And the graph that I'm looking here at here has no weight on the vertices. And again, this is something we look at later. Now, this is an interesting measure. It's what's called the K-core. So this is another way, this is another graph level measure, although it uses properties of vertices. So what is a k-core? So suppose you have a graph and potentially oriented. Okay, so that first definition, if you look, uses XU. What we call a k-core of G is a maximal subgraph in which each vertex has degree at least k. So this is not necessarily very easy to understand, but I will show you an example in very soon. And then when we look at a vertex, we can determine its coreness. And the coreness of a vertex is the largest value of k-core it belongs to, essentially. Okay, so look at the definition. The coreness of X as a vertex is k if X is in the k-core of G, but it's not in the k+1 core of G. Okay, so the highest k-core value of a vertex is its coreness. And again, as always, if you're looking at a directed graph, then you're going to look at in-cores or out-cores, because it depends on whether you're looking at in degree or out degree. Now, coreness has a function in R that we're going to use in a second to illustrate. But before I do so, let me show you coreness, some example of coreness. So this is the directed graph we've been playing with. This is G1 in the example, in the numerical example. So if I look at the in-core and out-core of this graph, I find that G has only a one core and a one in-core and a one out-core. Okay. And if you look at the degree of some of those vertices, whether you're looking at the in or out degree, there are vertices that have an in or out degree that is larger than 1. This is not what k-coreness is saying. K-coreness is I have a subgraph, which is maximal in the sense that I can't grow it more, but I have a subgraph in which each vertex has degree at least k. Okay, so it's not... well, I mean, I'll show you an example in a second where the things are a bit different. Let me first show you how you would do the computation here. And that's quite simple. So as I said, the function for coreness is coreness. So if I look at coreness for G1, and again, the mode is important because this is a directed graph. So let's look at in. And this is precisely what I was saying here. Okay, the coreness for this graph here is 1. The coreness in the out degree is also 1. Actually, if we look in both directions, you're going to see that it becomes different. So this is essentially the undirected case, and here the coreness becomes 2. Okay, so let me continue here. The first thing I want to do is to modify the graph a little bit. If I modify this graph a little bit by adding return arrows, okay, so here, for example, you can see that I can go from x2 to x3, but I cannot go back into x2. I can go from x3 into x6, but I cannot go from x6 to x3. Now let me assume that we have, additionally to these things we had before, we have these back arrows here that I've indicated. Back from x3 into x2, back from x6 into x3. Now what happens is that now the coreness of these three vertices is 2. So why is that? So you have to sort of use the degrees to see that. So the degree of x2 here in this graph, the out degree, let's look at arrows going out. So the out degree of x2 is 1, 2. The out degree of x3 is 1, 2. The out degree of x6 is 1, 2, 3. But remember, I'm looking for, so in terms of out degrees, I could have 2, 2, 3 here. But I'm going to make a subgraph, and I want this subgraph to have the vertices in there having out degree at least 2. So when I make a subgraph, what I do is I keep only the three, well, in this case, the three vertices that I'm interested in. I forget about the others. It's a subgraph. So any vertex that I remove, well, that I don't consider, all the arcs that are going to or are coming from these vertices are deleted. So the subgraph corresponding to x2, x3, and x6 is the one shown here. Any arrow in or out, well, in from outside or to outside of this subgraph of those red vertices is ignored in the subgraph. So that means that when I've selected x2, x3, and x6, then I have vertices, and here I'm just showing their I think I'm looking in the in corners, so I'm looking at in degree. And so here I'm looking at in degree of these three vertices. This is their degree, in degree. And you can see the in degree of this one is 1, 2. The in degree of this one is 1, 2. And the in degree of x6 is 1, 2. So there I have a subgraph where each vertex is connected to other vertices in that subgraph and has degree no less than 2. I could add a loop on x3. x3 would have degree, would have degree 3, in degree 3, if I added a loop on there. But the largest value for the maximal, when I'm looking at the maximal subgraph, when I'm looking at just those 3, wouldn't change, because that guy would have a degree larger than k. Okay. So k-corners is very important because it signifies that the vertices in this subgraph that you obtain are well connected. Okay, they're better connected than the others. They'll achieve a better circulation of information. I mean, as I said many times in graphs, it's important to think of things in terms of how does information flow. And here, those vertices are better connected, therefore the flow of information between them is better. If we look at the undirected case, now I've taken our original graph and I've removed directions. So this is the graph that I get. And that's what this numerical example was showing you. You see, when I'm doing corners mode all, what I'm looking at is this graph here. Sorry, excuse me. And this graph here, all the vertices have degree 2. Or at here, some of those have degree higher, but they have degree at least 2. Because this one has degree 4, this one has degree 4, but their corners is 2. And if I add a loop on this this middle vertex, which is x3, if I remember well, if I add a loop on x3, then I am even more connected, and those 3 vertices now form a 3-core. Okay. So again, this is something we'll see in a practical example very soon. But next lecture, I think. Okay. Now we're going to get to something that is has become one of the most important ways to look at graphs. And that is what is called vertex centrality, typically vertex centrality. So this is a vertex relative vision of things. So centrality, essentially, the question you're trying to answer is, what are the most influent vertices with respect to a variety of ways of thinking about what influence means, okay? But that's what centrality means. So actually, you will see often degree used as a measure of centrality, and you can see how this is going to indeed play out, because a vertex that has a very high out degree, for example, has the capacity to propagate information to a large number of other vertices. Or likewise, a vertex with a very high in degree is going to receive information from a large number of vertices. And so these are very central vertices as compared to vertices that have a very low centrality, degree centrality. Okay, so degree is essentially a measure of centrality. I'm going to, for the moment, show you just two other measures of centrality. We'll see more a little later in the course. Okay, there's not, just in passing, there's not that many lectures left. I think we're about down to 6 perhaps now. I'm a little puzzled as to what I'm going to do. I'm going to do some examples. I want to do a few other types of centralities. If you have specific things you want to see, perhaps you can tell me, because for the moment, once I'm done with those centralities and another type or two of centralities, then we're essentially done with the program for the course, and we probably have 1 or 2 lectures left when that is done. So if you have ideas about things you want to see, don't hesitate to let me know. I'll see if it's possible. Okay, so aside, the 2 types of centralities I'm going to show you here are betweenness and closeness. And as I point out, we'll come back to centralities in sort of applications and sort of perhaps more organized visions with more details on some of those types of centralities. But, and I should point out, for assignment 10, the 2 centralities we are going to see today are the only ones you need to know, on top of whatever is before. Now, betweenness. Betweenness is a very important measure, and it's a little complicated to get around. And so I'm going to spend quite some time showing you examples of this, and then we'll switch over to the numerics to see how it works. But I want to really explain what it is. Betweenness is a very interesting type of measure. There's a few definitions. The one I'm going to use is a very classic one. I think if you go to Wikipedia and check betweenness, that's the one you get. It's a very classic, but even you'll see that different algorithms to compute betweenness are going to produce different results, which is a little infuriating at times, but I'll get back to this. So suppose I have a graph, directed or not. Of course, as usual, if it's directed, things are a bit more complicated, but they're also a bit more realistic, and etc. Okay, so take a vertex X in the set of vertices. Oh, take a vertex X and I say the betweenness of V. So take a vertex V in the set of vertices, then the betweenness of V is this number that I'm writing there. That number is the sum of, okay, so this is a sum that runs for 3 different indices. Well, I mean, no, I should say for 2 different indices. And those indices are not the same as the index of the vertex that we're considering. Okay, so we are considering 2 indices that are different, and both are also different from the vertex under consideration. So it's the ratio, so it's the sum of the ratios. Okay, it's not each one of those ratios is summed for each different pair of vertices S and T that are not the vertex under consideration. We take the ratio of this quantity, sigma index ST of V, divided by sigma ST. So sigma ST, let's start with a denominator. Sigma ST is the number of shortest, typically geodesic, but you can also use a weighted distance. But for most cases, it's actually easier to think in terms of geodesic paths. So sigma ST is the number of the shortest geodesic paths from vertex S to vertex T. And remember, we are changing them. So we're taking all pairs of vertices in the graph. And sigma of ST of V now is the number of those geodesic paths that actually go through the vertex V. So what you're looking at is the ratio of the number of shortest paths that go through the vertex you're considering over the number of shortest paths between 2 vertices. And I'll show you this on an example, okay? But so this sounds complicated, but you'll see it's quite easy. I mean, it's easy to grasp, at least, when you think about it. So in words, we take every pair of vertices S and T, and we compute the shortest paths, plural, I mean, there can be several, between them. And then for each pair of vertices, we determine the fraction of the shortest paths that pass through the vertex we're considering. And we sum this fraction for all pairs of vertices that are not V. I think, yes, before I go any further, and oftentimes you will see, and the example that I will show you numerically do this, you will see that we will normalize betweenness often by dividing through the number of pairs of vertices that don't include V. So potentially. So for dividing through the number of pairs of vertices, this is not written well. This is, okay, so this is how far you are from having a complete graph. So if I had a complete graph not including one vertex, then it would have n minus 1 and minus 2. Remember that the number of arcs in a complete graph with n vertices is n times n minus 1 in the directed case, and n times n minus 1 over 2 in the undirected case. Here, what we're doing is we're removing one vertex from this graph, and we're saying, okay, so in total, there could be that number of not vertices, that number of arcs or edges. And that's what we normalize by. Okay. So let me show you an example. First of all, let's look at our usual suspect graph. So this is the graph. And here, just in passing, so let me go back to the numerics now. I can take this graph, and this is actually G1. So by the way, so you see how to compute all the distances between all the vertices. That was one of the questions in assignment 9. Well, now you have the solution to this is simply to use the function distances. So to use the function distances, when you use the function distances, what you get is this. So this is saying that is the shortest, the length of the shortest path. Let's look at the first row, for instance. This is the length of the shortest paths from 1, vertex x1, to all the other vertices. Okay, so to go from, and remember, we're not counting distance from one vertex to itself. So vertex from x1 to, distance from x1 to x2 is minimum distance is 1. From to x3 or x4 is 2. To x5, which is further down in the graph, is 4. And to x3, the minimum distance is 3, etc. Okay, so you can, this function gives you this. So we have the number of, we have the length of the shortest paths. And if we wanted to compute the betweenness without using the R function betweenness, then what do we need to do? We need to find the number of shortest paths between each pair of vertices. And we need to find the number of those shortest paths that do not go through a given vertex, the vertex we're considering. So we found this matrix. We were looking for, so one thing we can do easily is find the number of shortest paths between pairs of vertices. The reason we can do this easily is that, first of all, when we look at this distance matrix, one information we get is that the longest shortest path is 5. Okay, there's a few cases where I can find a shortest path of length 5. So I know that if I take, if you recall, when you have your adjacency matrix A, when you take A squared, this is going to give you the number of shortest paths of length exactly 2. A cubed is going to be the number of shortest paths of length exactly 3, and so on and so forth. Okay, but here I know that my number of shortest paths is not going to be larger than 5. Okay, because all my vertices have at most a distance of 5 between them. So what I can do is take the powers of my my matrix A, my adjacency matrix, and when, for example, I'm looking for the number of shortest paths of length exactly 2, here I can simply pick that corresponding entry in the matrix A squared. When I'm looking for the number of shortest paths of length exactly 5 from vertex 1, 2, 3 to vertex 4, then I can take the entry in A to the 5, because this minimal length is 5. So I can take the entry in A to the 5 and select that. Okay. And we find this. So let me, because maybe that's worth illustrating. So let me show you that this is done very, very easily. Okay, I'll code this right here. I'm going to call this distance matrix D. And then what am I going to say? I'm going to, for instance, what can I do? I could say, well, let me make powers. Yes. There's a library, but I like to load libraries at the beginning of my code, but library. If you want to take the powers of a matrix, the best is, of course, it doesn't you install package. If you want to take the power of a matrix, this function has, this library has something that is very convenient. It's done. Okay, so now I can comment this out. Okay, so now I have the package XM. So what am I going to do? I'm going to say that, let's say powers A is a list. And what I need to do is say that powers A, well, first of all, of the first matrix is simply A1. We called it A1, right? A1, yes. So powers of A is my degree 1 matrix. And then what I'm going to do is I'm going to vary K, let's say, from 2 to 5. Remember that the maximum that I find in this matrix is 5. So from 2 to 5, I'm going to do that powers of A of K equals. So this is what XM as a library allows you to use. It's this notation, which is simply that it's the power. So this is A1 times A1, A1 times A1 times A1, etc. The power notation. Okay. So if I do this, let me run this code. Then, for instance, I could have powers of A of 3. So that's the longest, shortest paths. Sorry, that's the number of paths of length 3 between pairs of vertices. So if we go back to this graph, for example, you can see that I'm looking here at, let's say, from here to there. So how many paths of length exactly 3 are there between vertex 1, let's say, and vertex 2? Well, there's, where am I? Path of length exactly 3. Well, I can go go here. There's 1 where I'm doing this. Okay, so path, I'm going x1, x2, x2 by going around the loop, or I'm looking at 3, okay, by going around the loop twice, or I'm going 1, 2, 1, 2. Okay, so there are 2 paths of length exactly 3 in this graph between 1 and 2. This is what this is saying. Okay, now what do I need to do? Well, now I'm going to call minimal distance, number of shortest paths. Let's call it sigma st. Okay. Well, it's a matrix, so I'm just going to use a little trick. I want to make a matrix of the same size as A1 in this case. How do I, but full of zeros? Well, I can just multiply A1 by zeros, by 0, sorry, and that just gives me the 0 matrix. This is a sort of shorter thing. And what am I going to do? I'm going to say that for all the rows in sigma st, and for all the columns in sigma st, sorry, dimension of sigma st of 1, because these are the rows, dimension of sigma st of 2 columns. What am I going to do? I'm going to say that sigma st of, that entry, that could be ij, okay, I like to use r and c. Sigma st of r and c is what? Well, I need to go look in this matrix that I have here and see how long the path is. So here, for example, the path is of length 1. And so when I have a path of length 1, what do? I get my information in powers of A of what? So powers of A, the index of K here is given by D of R and C. Let me say that we don't care about diagonal entries. So if R is not equal to C, if it is equal, we don't bother. Okay, so if R is not equal to C, then this is what we get. I don't know why it's... so the power that we need to look at is the one that's indicated here. Okay, so if here I have a path of length 4, then this is what I look for. So this is power of D of RC. And still, I'm looking at that matrix A to the K, the entry RC. And so here, in principle, if I haven't messed up, we should have sigma st. Let's run this code. And not surprisingly, because this graph is very simple, yes, so that ran as it should. If you think about it, this graph is very, very simple. So whenever I'm looking at, for example, there's a path of length 4, the minimum distance between 1 and 5, this guy, is 4. Well, how do I get this one? There's only one way to do it. I go from here to there, to there, to there, to there. Okay, so there's only one such path. When I'm looking at longer paths, of course, I'm going to have more choices. But here, there's no fork in the road. For instance, if I had the possibility of going from x1 to x3 directly, things would be different. But here, there's no fork in there. Or let's say x. Okay, so maybe just for illustration of this so that you understand what's happening, just briefly let me, of course, this should be made as a function because, I'm going to illustrate here because it's going to be bad. I'm going to do the things that I always tell my students not to do, my graduate students or my postdocs or people working with me. You should not do what I'm about to do, but this is for illustration purposes. Let me take A1, just so you see what I mean. So let me take a matrix A3, and what I'm going to do is I'm going to add an arc from x1 to x4. This is going to make things more interesting because if I have an arc from x1 to x4, you can see that to get to x3, I have two shortest paths. I can go from x1. I can go x1, x2, x3, or x1, x4, x3. Okay, so this is going to be a slightly more interesting graph. I'm just going to add a 1 here. Then I'm going to say that G3 is this. So as I said, this is really ugly. I would probably persecute my students, my postdocs, etc., if they were to do this. But let's do this quickly and let's see if this works. Yes. So now you see, so I've added, yes, I've plotted. I've added an arc from 1 to 4 here. And you can see that now the sigma st has become more interesting. Well, it's not sigma st, sorry. This is not quite sigma st. I shouldn't call it sigma st because then I have to sum things to get sigma st. Exactly. No, actually, here I get sigma st. Yes. Complicated, these things. But okay, so you can see now that to go from 1 to 2, to 3, sorry, I have two shortest paths. Okay, because of this fork along the road that I've introduced, where you can either go 1 to where did I? Yes, sorry, 1, 2, 3, or 1, 4, 3. And just that has made the problem more complicated in terms of the graph. Okay, so where am I? Yes, I've just computed this, and that's the matrix we found. And recall that now if I want to compute the betweenness, so here we've dealt with this one. Okay, we've dealt with sigma st, but what about sigma st of v? And that becomes more complicated, and this is one that we cannot resolve by just using the matrix. We have to use a shortest path finding algorithm, such as Dijkstra that you did in the assignment, or other shortest paths. I'm doing something stupid here. And so, for example, here, what we would use is this function here, all shortest paths. And let me show you how this works. And I'm actually going to use this new matrix that this new graph that I created because it's a bit more interesting than the original graph. So all shortest paths is going to give you the number of shortest paths. No, sorry. It's going to give you the shortest paths between pairs of vertices. So let me take G3, this graph that I just created, because it's more interesting. Let's look for the shortest path from vertex 1 to vertex, which one is it that I want to look at? Or let's take 3, because it's the first one where we're going to observe some difference. Ah, I'm missing the underscores. Okay, so you can see what's happening here. So we have two results from 1 to 3. We can go 1, 4, 3, and we can go 1, 2, 3. Okay. Number geo, I'm not entirely sure what that is. I'll have to check it out, or I recommend that you actually look at the help. But what's important here, if I were looking for the betweenness of, say, 2, when I'm computing sigma st of v here, then I am going to be looking at what the shortest paths are. Yeah, I've got the forbidden thing. Let me reload. Oh gosh, I don't know why this thing doesn't remember my password. It's a little annoying. Yes, I save it, but I know it's not useful. So you can see what's going to happen when you're trying. I mean, if you were trying to use that function directly yourself, as I said, there's a R function that in iGraph that does exactly that computation without you having to worry about doing this. But it's important to see what sort of the innards of the function are. And so that function shortest path, if I was looking at vertex 2, for instance, I would look for all the shortest paths. When I'm computing this sigma st of v, I would look for all the shortest paths where 2 is one of those vertices, okay, in the list. So this one I would exclude. It's not part of the computation of sigma st of v. It would be part of a computation, of course, of sigma st, because this is a shortest path, and we count all the shortest paths. Okay. So to give you an example, and now using the proper function in iGraph, so without going through all of this, but as I said, I think it's important to... why is it? Okay, so this says directed equals false. I don't think it's the direct... I thought I had 2. Okay, I have a problem with my slides because I think that's the directed case. No, that's the undirected case. This should be... Okay, let's check. So we are not going to do... We're not going to do G3, we're going to do G1 to begin with, betweenness of G1. So directed will be true. I believe that's not the between, and let's normalize. Okay, so I'll show you the what the output is when you don't use normalize, but let's start with normalized. Yes, indeed, this is directed equals true. Normally I have another slide which shows you the same graph but without the directions. I don't know why I messed up here. So these are the numbers that you're seeing here. And let me point out this vertex here, vertex number 4. So here I'm plotting things with just the betweenness of those vertices rather than their name. I probably should put both. But look at vertex x4 here, which is that lower vertex with a 0. Why is its betweenness equal to 0? And that's really important. Okay, that shows you why betweenness is such an important quantity. If you look at this graph, that vertex x4 here, it's on none of the shortest path between other vertices. Of course, when you consider x4 going to other vertices, x4 is on those things. But if you exclude x4 as a vertex to go through, if I'm trying to go from here to there, well, I have no interest. If there is a choice, if I'm going to from x1 to x3 or x1 to x5, 6 or 5 or whatever, I have no interest in going through that vertex because it makes my path one longer. Okay, so there's no configuration in which going through x4 is beneficial. So that means its betweenness is 0. It's a place that is not important. It's like if you're thinking about, I don't know, take the Trans-Canada Highway and take a side road somewhere that goes to some place, but is not on the Trans-Canada Highway. The betweenness of that place would be 0. Okay, there's no reason to go there. Unless you're visiting someone there or something like this, but there's no reason to go through that vertex because it is out of the way. It always introduces a longer path. Okay? And actually, so this is, so let me first show you what happens if you're not normalized. Okay, so Control Z, maybe what I should do is instead of that, I should put both. So you see that whether it's normalized or not, the value of the betweenness of that remote vertex is still 0. Okay, so one is normalized by being scaled down, as I indicated here. Where is that? Scaled down by seeing how far away, looking at the density in some sense. Okay, how far away from being dense the graph is if you consider the rest of the graph, and the other is not normalized. Okay, and you will see this is actually a little frustrating if you use iGraph. This is the type of results that you would get. If you use another package for graphs in R, then you might get slightly different results. It's always very, very important when you're using these packages to look at what definition they're using for such measures as betweenness. The good thing is that the measures are comparable if you're using the same function. Okay, but beware of comparing measures using, like, I don't know, you're doing some computations on Python for some work and then you're doing some computations on R for some other work. if there's a function betweenness in both and you're not using the same package, because remember, iGraph exists in both Python and R. But if you are not doing this, then you might end up in doo-doo because the results you get are not necessarily comparable. They're comparable within the context of one function. They're not comparable between functions. So be very careful about this. Just actually, so maybe to illustrate, now let's look at G3 that I just created, that graph that has this fork in the road. And you're going to see that the betweenness of that vertex x4 there, or x, yes, I think it's x4, but betweenness of that vertex x4 is not going to be 0 anymore. Okay, so you can see now it's still not a very important vertex because there's typically other ways to do things, but it has risen to a higher degree than it used to be. And actually, its betweenness is now, when you look, it's possible to do things going through 2 or going through 4. And this is reflected here by the fact that the betweenness of 2 and 4 is now the same. So 2 has become less important. 4 has risen in importance because it's now possible to take both vertices to achieve a certain direction. And let me just point out, just maybe to finish here on betweenness, of course, if you look at the undirected case, things are a bit more complicated. Well, I mean, not more complicated, but they're also so. And interestingly, here, oh no, it's still 4. So 4 is still the vertex with betweenness 0, which again makes sense because even if I have undirected arrows here, it still is going out of the way if I'm going through this vertex. One thing that I wanted to do, perhaps I should show you this quickly. Let me look at extreme cases. Just so you see what's happening for betweenness. So I am going to first make a very simple, let's call it A4, and I need to take the thing that makes the graph as well. Okay, so G4. Okay, so let's make a graph where, let's make a line. Let's first see if I can manage to make a line. So from 1 I can go to 2. From 2 I can go to 1, or I can go to 3. From 3 I can go to 2, or I can go to 4. From 4 I can go to 3 or 5. From 5 I can go to 4 or 6, and from 6 I can go to 5. Let's leave that one like this. Yes, I have what I wanted. So this is a line graph. It doesn't show as a line, but you can go in all directions, and actually when you get to 6 you can also loop here. Now let's look at betweenness here. Let me just copy this. Okay, so, and this is a very common thing. Okay, so the betweenness of 1 and 6, even though 6 has a loop, okay, it doesn't change this, is 0. And you can think of these things as, well, they're at the end of the road. Okay, so this sort of makes it very easy to understand what's happening if you look at it this way. Okay, this is a graph where if you there's no shortest path out of 1 or 6, well, through 1 or 6, sorry, that are actually a shortest path between any other pair of vertices. So if 6 is there in the computation of shortest paths, it is because you're looking at vertex 6. You can't have vertex 6 as a shortest path for any other shortest path. Okay, there's no shortest path through 6 that doesn't involve 6 itself in terms of one of the endpoints. And let's modify this just a tad. So I'll just copy and paste this. Let me make a matrix. Now let's do a matrix, but where when I from 1, let me do a circle. So when I'm in 1, I can also go to 6. And when I'm in 6, I can also go to 1. So now this graph is going to be a circle, okay, two-directional circle, and I'll let you guess what's going to happen. If you think about it, okay, I have a circle, and any vertex that I pick in this circle is going to be on as many of the shortest paths as the other vertices, okay? Because that graph, the way you go around it is not important. So the graph is indeed like this nice little thing, and as you can see, the betweenness is the same for each vertex. And we would see the same thing, for example, if we were to create a complete graph, because the idea would be the same. If I have access to all vertices, then the shortest path from me to any other vertex is just going from me to that other vertex. And so and that graph would be the centrality, the betweenness would be 0, I believe. 0 or very small. Let me see. So how? No, it would be 0. All the vertices would have betweenness 0, because if you think about the shortest path between any two other vertices would never involve a third vertex, because all the vertices are connected to each other. Okay, and one last thing I want to go over. It looks like I'm doing good for time, which also means that, once again, I apologize. The video is going to take some time to be converted, and therefore it will be posted in a little late today. Is closeness. So closeness is a bit the same as betweenness, except that here you're looking at the distance between vertices. So in a sense, when you're looking at the closeness of a vertex, you're looking at how far it is from all the other vertices. So it's a different measure from betweenness. Betweenness says how often do other vertices have to use you as a transit point. Closeness says how far are you from the other vertices in the graph. Okay, so it's the mean distance between you and all the other vertices. And again, closeness is going to come out with different definitions depending on precise definitions. I mean, the overall definition of closeness is always the mean geodesic distance, but the precise look of closeness is going to depend a lot on the function that you're using to create it. It could be defined this way. N here, I should point out, N is the number of the order of the graph. or it could be 1 over this quantity. It varies. And here I've simply, so closeness also has a function in R, and maybe I could do closeness. Let me copy this and show you the closeness for the different, of course I need to change these things. So closeness of G1 is, this is what I'm showing you here. Let me do, what was this? G4 and G3, G4 and G. We need another one. And this is oriented, of course, so the distance is important. G3, G4, and G5. 5. And just in passing, that nice graph, the ring that I did at the end, you can see that indeed, if you're thinking about what the closeness means, it's the mean distance to all the other vertices. Well, if I'm in 6, my mean distances to the other vertices is the same as that in 5 to all the other vertices, because this graph is just itself replicated many times. Okay, whereas this one has a very different looks, and you can see that the terminal vertices that had betweenness of 0, they also have the smallest closeness because they're at the endpoints, whereas the central vertices, because I've chosen an even number, so it's normal that I have 2 like this. The central vertices are more central and they have access to more vertices. If I had taken a line graph of 5 vertices, I would have 1 central vertex. I mean, the central vertex would have the highest closeness, and the other vertices would match. Okay. And I think that's all I want to. Oh, no, yes, that's all I want to do today. As I said, I apologize. This is going to come a little late because now I'm in for about an hour and something to process that video. But okay, better late than never. So next time, I'll actually show you some proper, real example of a graph. Something out of the real world, not some arbitrary example like the one here.